Autumn 1877. Winter already whispers down from the Cascades as Jonas Christofferson walks through cedar-rich woods along the Columbia River. While every settler races to build standard log cabins before snow falls, this Norwegian immigrant stops at a massive dead cedar, hollowed by decades of rot, 8 feet across, 30 feet long, its thick walls still intact and weatherproof. His neighbors call it wasteful. They call him a fool. "Why waste fine timber on a dead tree?" they scoff. Standard cabins use hewn logs, notched corners, chinked with clay. That's what everyone does. But Jonas clears the hollow interior, fits rough planks, adds a small iron stove. He spends months on what others dismiss as a bear den. Then January 1878 arrives. Temperatures plummet to 15 below zero. Blizzards bury cabins to their windows. Standard log cabins crack and leak. Families burn through firewood desperately. But inside that fool's hollow log tunnel, 30 degrees warmer than outside. What did this immigrant understand about cedar, thermal mass, and survival that everyone else missed? If you value stories of practical wisdom that stood the test of time, make sure to subscribe. We've got more documented accounts worth remembering. The ridicule began before Jonas even started clearing the debris from the hollow cedar's interior. Samuel McLeod, a sawmill foreman who'd built 3 cabins in the valley, shook his head as he watched the Norwegian immigrant measure the circumference of the rotted Heartwood. 8 feet of prime cedar timber, McLeod muttered to anyone who'd listen. And he's treating it like a cave. The other settlers agreed. Why hollow out a perfectly good log when proper construction meant felling trees, hewing them square, and notching corners the way their fathers had done back in Ohio and Missouri? But Jonas saw something entirely different when he peered into that cedar's hollow core. In the mountain valleys of western Norway, where winter temperatures dropped to 20 below and stayed there for months, his grandfather had taught him that the thickest walls weren't always the strongest. They were the smartest. Dense wood, even dead wood, held heat like stone held warmth from summer sun. The cedar's outer shell measured nearly 2 feet thick in places, seasoned by decades of Pacific Northwest weather into something harder and more weather-resistant than fresh-cut lumber. The hollow interior, protected by that thick shell, remained bone-dry despite the autumn rains that had other settlers worrying about their green log walls. Jonas had learned his building wisdom during childhood winters when his family heated their stone and timber farmhouse with a single fireplace. His uncle Eric, a carpenter who'd survived the brutal winter of 1856, had shown him how to bank fires for maximum heat retention and how thick walls created thermal mass that evened out temperature swings. Wood is like a battery for heat, Eric had told him, but only if you use it right. The old Norwegian methods weren't about speed or convenience. They were about surviving when fuel was scarce and mistakes meant death. While his neighbors spent September and early October racing to complete their standard 12 by 16-foot log cabins, Jonas worked methodically inside his cedar tube. He cleared out decades of accumulated forest debris, soft, punky wood, and the remnants of small animals' nests. Using a combination of axe work and careful burning, he removed the rotted heartwood until the interior measured roughly 7 feet in diameter, enough space for a sleeping platform, a small cooking area, and storage. The length of 30 feet gave him room to section off different areas, living space near the entrance, sleeping quarters toward the back, and storage for firewood and supplies. The construction details that drew the loudest criticism were precisely what Jonas considered most essential. Where conventional cabins use single log walls chinked with clay and moss, his cedar shell provided continuous insulation without gaps. He built a raised plank floor using rough-sawn boards purchased from McLeod's sawmill, creating an airspace beneath that would prevent ground moisture from seeping up. The entrance required careful engineering, a frame of thick planks fitted snugly into the cedar opening, hung with a door made from 3 layers of 1-inch boards. Most importantly, he positioned his small iron stove near the center of the tube rather than against one wall, allowing heat to radiate in all directions. Rebecca Larson, whose husband was struggling to chink the gaps in their hastily built cabin, stopped by one October afternoon to watch Jonas install his stovepipe. "Looks like you're building a root cellar that someone forgot to put underground," she said, though without the malice that characterized most comments. Jonas explained his reasoning. The thick cedar walls would hold heat like the stone foundations back in Norway, while the tube shape would circulate warm air more efficiently than a square room. Rebecca listened politely, but her expression suggested the same skepticism shared by everyone else in the settlement. The mockery intensified as October progressed, and Jonas continued working while other families had already moved into their completed cabins. Tom Galloway, an elder settler who'd been in the territory since 1846, proclaimed that Jonas was making a job that should take 3 weeks stretch into 3 months. Children from neighboring families began calling his project the Bear House and daring each other to peek inside the hollow opening. Their parents found this hilarious, reinforcing their belief that the Norwegian was wasting time and materials on an impractical experiment. What none of the critics understood was the precision behind Jonas's seemingly simple approach. Every measurement reflected hard-won knowledge about heat retention and airflow. The 7-foot interior diameter wasn't arbitrary. It provided enough space for daily activities while keeping the heated air volume manageable. The 30-foot length created natural temperature zones, with the warmest area near the stove and cooler sections for sleeping and storage. The raised floor prevented heat loss to the ground, while the curved walls eliminated cold corners where frost typically accumulated in square rooms. By late October, as the first frost touched the valley, Jonas had completed his hollow log shelter. The entrance was weatherproofed with tar and oakum, the stovepipe extended through a carefully sealed hole in the cedar wall, and interior walls were lined with split cedar boards for smoothness and additional insulation. He'd spent 2 months on construction that his neighbors had completed in 3 weeks, used materials they considered inferior, and created living space they found cramped and cave-like. Samuel McLeod made a final inspection before winter set in, running his experienced carpenter's eye over Jonas's work. "I'll grant you this," he said grudgingly. "It's built solid. But come February, when you're burning through a cord of wood every 2 weeks trying to heat that tube, you'll wish you'd built a proper cabin with proper windows and proper ventilation." The other settlers nodded their agreement. They'd done things the proven way, the sensible way, the way that generations of American frontiersmen had built homes in the wilderness. As November snow began dusting the Cascade Peaks, the hollow log tunnel stood ready for winter's test, surrounded by conventional cabins whose builders remained confident they'd chosen the superior approach. The first test came on January 8, 1878, when an Arctic front swept down from British Columbia, bringing temperatures that would hover at 15 degrees below zero for 6 consecutive nights. What had seemed like a typical Pacific Northwest winter suddenly turned into something that reminded old-timers of the brutal seasons they'd fled when leaving the upper Midwest. Snow began falling on the 6th and didn't stop for 36 hours, accumulating 18 inches in the valley and driving against cabin walls with winds that found every gap in hastily chinked log construction. Samuel McLeod discovered the first serious problem on the morning of January 9th, when he woke to find frost covering the inside walls of his cabin 3 feet from his fireplace. The green logs he'd used in his rush to complete construction before winter had dried and shrunk in the extreme cold, opening gaps between the courses despite his careful chinkling with clay and moss. Cold air poured through these cracks, creating drafts that made it impossible to heat the interior above 40 degrees, even with his fireplace roaring constantly. His family huddled around the hearth wrapped in every blanket they owned, burning through split firewood at a rate that would exhaust their winter supply by March. The Larson family faced similar struggles in their 16 by 20-foot cabin. Rebecca had noticed hairline cracks appearing between the logs by early December, but the sudden temperature drop widened these gaps into channels that whistled with wind. Their windows, covered with oiled paper rather than expensive glass, provided little insulation against the cold. Despite burning nearly a cord of firewood in the first week of January alone, frost continued forming on the interior walls each night, creating dampness that soaked into their bedding and clothing. Their 2 young children developed persistent coughs that worried Rebecca, who recognized the symptoms of the lung sickness that had killed settlers throughout the territory. Tom Galloway's cabin, built with more experience and better materials, fared only marginally better. His logs were better seasoned and his chinkling more carefully applied, but the extreme cold still found ways through the construction. He estimated he was burning 60% more firewood than anticipated, forcing him to venture out in dangerous conditions to retrieve logs from his woodpile. At age 54, the physical strain of constantly feeding fires and hauling firewood in sub-zero temperatures was taking a toll he hadn't expected when planning his winter supplies. Meanwhile, inside Jonas's hollow cedar tunnel, the thick walls were performing exactly as he'd anticipated. The massive wooden shell, seasoned by decades of weathering, absorbed heat from his small iron stove and released it slowly and steadily throughout the long winter nights. While outside temperatures plummeted to 15 below zero, the interior maintained a consistent 48 to 52 degrees with minimal fuel consumption. The curved walls created natural air circulation that distributed heat evenly throughout the 30-foot length, eliminating the cold spots that plagued conventional cabins with their square corners and flat walls. The thermal mass effect that Jonas had learned about in Norway was working precisely as his grandfather had taught him. During the day, when he kept a moderate fire burning, the thick cedar walls absorbed excess heat. At night, when he banked the coals and let the fire die down to conserve fuel, those same walls slowly released their stored heat, maintaining comfortable temperatures with minimal additional firing. He was burning less than half the firewood that his neighbors consumed, yet staying consistently warmer and drier. The first neighbor to notice the difference was Rebecca Larson, who walked past Jonas's shelter on January 12th while hauling water from the creek. She observed that only a thin wisp of smoke rose from his stovepipe, while the chimneys of conventional cabins poured thick columns of smoke into the frigid air as their owners desperately tried to maintain heat. Curious and increasingly desperate about her own family's situation, she accepted Jonas's invitation to step inside and warm herself by his stove. The contrast was immediately striking. Where her own cabin felt damp and drafty despite the roaring fireplace, Jonas's tunnel remained dry and remarkably comfortable. The temperature difference was so pronounced that she had to remove her heavy coat within minutes of entering. The air quality was cleaner too, without the smoky atmosphere that characterized her own cabin where downdrafts occasionally blew smoke back into the living space. Most impressive was the silence, no wind whistling through cracks, no creaking and settling as green logs continued shrinking in the cold. Tom Galloway accepted a similar invitation 3 days later, after a night when his cabin's interior temperature had dropped to 32 degrees despite continuous firing. Inside the cedar tunnel, he found Jonas working comfortably in his shirt sleeves, preparing a hot meal on his small stove. The older settler, who had survived many harsh winters in the territory, immediately grasped the engineering principles at work. The thick, dense wood was acting like the stone walls of European castles, storing and releasing heat in a way that thin log walls simply couldn't match. Word began spreading quietly among the settlement's families. Samuel McLeod, despite his earlier criticism, found himself walking past the hollow log shelter more frequently, noting the minimal smoke output and the comfortable sounds of normal daily activity coming from within. His own family was rationing firewood and sleeping fully clothed to conserve body heat, while Jonas appeared to be living through the same brutal weather without hardship or privation. By the third week of January, several families had begun experiencing more serious problems. The constant moisture from melting frost on interior walls created conditions for mold growth, spoiling stored food and creating health hazards. 2 families with elderly members were burning through firewood so rapidly that they faced the real possibility of running out before spring, forcing them to consider abandoning their claims and seeking shelter in town. The hollow cedar tunnel, meanwhile, continued performing flawlessly, its ancient wood proving superior to modern construction methods in ways that none of Jonas's critics had anticipated. The catastrophic storm arrived on February 3, 1878, beginning with heavy snowfall that would continue for 36 hours straight. What started as typical winter weather quickly escalated into the worst blizzard the Columbia River Valley had seen in living memory. By the morning of February 5th, 3.5 feet of snow had accumulated across the region, with drifts reaching 6 feet against the north-facing walls of conventional cabins. High winds followed the snowfall, driving the accumulated powder into every crack and crevice, while temperatures plummeted to 22 degrees below zero. The first structural failure occurred at the Henderson cabin on February 6th. The family had built their roof using rough-sawn boards covered with split cedar shakes, a construction method that worked adequately under normal snow loads but couldn't support the unprecedented accumulation. The saturated snow, compressed by wind and its own weight, created a load exceeding 40 pounds per square foot across their 16 by 20-foot roof span. At dawn, the main ridge beam cracked with a sound like a rifle shot, followed by the complete collapse of the eastern section. Margaret Henderson and her 3 children escaped injury only because they'd been sleeping near the fireplace on the western side of the cabin. Samuel McLeod's supposedly superior construction faced different but equally severe problems. His carefully chinked log walls, already compromised by shrinkage cracks, began failing catastrophically as snow melted and refroze in the gaps between logs. The expansion and contraction cycle widened existing cracks into channels that allowed snow and moisture to penetrate deep into the wall structure. By February 7th, water was actively dripping from the ceiling during the day, then freezing solid each night, creating an accumulating layer of ice on the interior walls and floor. The family's food supplies, stored in wooden crates along the walls, became sodden and began spoiling despite the sub-freezing temperatures. The Larson family cabin developed what Rebecca would later describe as a breathing wall phenomenon. The combination of wind pressure and temperature differentials caused the entire north wall to flex visibly during wind gusts, opening and closing gaps in the chinkling with each movement. Snow forced its way through these shifting openings, creating piles of ice and slush inside the cabin that never fully melted despite their continuous fireplace operation. Their 2 children, already weakened by respiratory problems from the damp conditions, developed fever and severe coughs that Rebecca recognized as potentially fatal pneumonia symptoms. Tom Galloway, the most experienced builder among the settlers, watched his own cabin begin failing in ways that contradicted everything he thought he knew about log construction. His seasoned logs and superior chinkling techniques had worked perfectly in previous winters, but the extreme conditions revealed fundamental flaws in conventional building methods. The clay-based chinking, frozen and thawed repeatedly, began crumbling out of the joints. His shake roof, loaded beyond its design capacity, developed multiple leaks that allowed melted snow to saturate the wooden floor and damage stored supplies. By February 8th, he was burning nearly a cord of firewood every 4 days just to maintain interior temperatures above freezing. The breaking point came during the night of February 9th, when a second wave of the storm brought sustained winds exceeding 40 miles per hour. 3 more cabins suffered partial roof failures, while 2 families with elderly members made the desperate decision to abandon their homes entirely. The Williamson family, their cabin flooded by roof leaks and their firewood supply nearly exhausted, loaded what possessions they could carry and attempted the dangerous journey to the nearest town 12 miles downriver. They would be found 3 days later, having taken shelter in an abandoned trapper's shack, suffering from severe frostbite, but alive. Meanwhile, Jonas's hollow cedar tunnel was demonstrating the superiority of its ancient engineering with quiet efficiency. The rounded exterior surface of the massive log caused snow to slide off rather than accumulate, preventing the dangerous loading that was destroying conventional roofs. Wind flowing over the curved surface created less turbulence and pressure than the sharp angles of traditional cabin construction. The entrance, sealed with his carefully fitted door and additional planking during the worst of the storm, remained completely weatherproof despite the driving snow and sub-freezing temperatures. Inside the tunnel, conditions remained remarkably stable throughout the crisis. Jonas's small iron stove, fed with split cedar and fir, maintained interior temperatures between 46 and 51 degrees even during the coldest nights. The thermal mass effect of the thick walls continued working perfectly, storing heat during the day and releasing it gradually through the long winter nights. His total firewood consumption since the beginning of winter measured just over 2 cords compared to the 4 or 5 cords that his neighbors had already burned through by early February. The true test of the tunnel's capacity came when Rebecca Larson arrived at Jonas's door on February 10th, carrying her youngest child and asking desperately for shelter. Her own cabin had become uninhabitable, with ice covering the interior walls and standing water on the floor despite their best efforts to maintain heat. Jonas immediately cleared space in the rear section of the tunnel, arranging sleeping areas for the Larson family using additional planking and wool blankets. The 30-foot length of the shelter easily accommodated both families without overcrowding, while the efficient heat distribution kept everyone comfortable. Tom Galloway joined them 2 days later when his own cabin's roof began showing dangerous signs of imminent failure. The three families, totaling 8 people, found that the Cedar Tunnel's heating system required minimal additional fuel to maintain comfort for the larger group. Jonas's precise understanding of thermal dynamics and air circulation, learned in the harsh Norwegian winters, proved that his primitive shelter could outperform conventional construction not just in efficiency, but in capacity and safety. By February 15th, the storm had finally passed, leaving behind a landscape of half-buried structures and a white settlement where nearly a third of the cabins stood abandoned or seriously damaged. The hollow cedar tunnel, visible only by the thin column of smoke rising from its entrance, had sheltered 3 families through the worst weather any of them had ever experienced. The spring thaw began in late March, revealing the full extent of the winter's destruction across the Columbia River Valley. As families emerged from their various shelters and makeshift arrangements, the damage to conventional log construction became undeniably clear. The Henderson cabin stood with its collapsed roof section still buried under compacted snow and ice, while water damage had rotted the exposed floor joists beyond repair. Samuel McLeod's cabin, though structurally intact, required complete re-chinkling and replacement of interior wallboards that had been permanently warped by repeated freeze-thaw cycles. The humbling began quietly. Rebecca Larson was the first to approach Jonas directly, asking not just for temporary shelter, but for instruction. Her family's cabin needed complete reconstruction, and she wanted to understand the principles behind his successful design. Jonas walked her through the thermal mass concepts he'd learned in Norway, explaining how the thick cedar walls stored and released heat more efficiently than thin log construction. He showed her the importance of the raised floor system, which prevented ground moisture from wicking up into the living space, and demonstrated how the curved walls eliminated cold corners where frost typically accumulated. Tom Galloway's request came with the measured respect of one experienced builder acknowledging another's superior knowledge. His own cabin repairs would cost nearly as much as original construction, and he wanted to understand how Jonas had achieved such remarkable fuel efficiency. Jonas explained the positioning of his iron stove near the center of the tunnel rather than against a wall, allowing heat to radiate in all directions rather than being lost through exterior walls. He detailed the importance of the entrance design, with its multiple-layer door and carefully sealed frame that eliminated drafts completely. By early April, word of the hollow cedar method had spread to settlements up and down the valley. Families facing expensive cabin repairs began searching the forest for suitable hollow trees, though finding specimens matching Jonas's original cedar proved challenging. Most of the ancient old-growth trees with naturally hollow cores had already been claimed for conventional lumber or were located in terrain too difficult for homestead development. This scarcity led to the first adaptations of Jonas's basic principle. The Morrison family, unable to locate a suitable hollow log, built what they called a cedar tube cabin, using techniques Jonas helped them develop. They constructed double walls of split cedar planks with 18 inches of sawdust insulation between them, creating a structure that mimicked the thermal mass properties of the original hollow log. The interior measured 8 feet by 24 feet, smaller than Jonas's natural tunnel, but large enough for their family of 4. Their fuel consumption that following winter measured approximately half that of conventional cabins, validating the thermal mass principle even in modified construction. Samuel McLeod, swallowing his considerable pride, approached Jonas in May with a proposal that surprised the entire settlement. Rather than rebuilding his damaged cabin using conventional methods, he wanted to construct a hybrid shelter that combined traditional framing with Jonas's insulation principles. Working together, They developed a design using a conventional rectangular frame, but with walls built from 2 layers of logs separated by a cavity filled with cedar bark and sawdust. The result was a structure that looked more familiar to other settlers while incorporating the thermal efficiency that had made Jonas's shelter so successful. The technique's adoption accelerated through the summer building season of 1878. 5 families in the immediate valley built variations of the hollow log or thermal mass design, while 3 more implemented modified versions of Jonas's heating system in their conventional cabins. The adaptations ranged from simple improvements like repositioning stoves away from exterior walls to complete reconstructions incorporating double-wall insulation systems. Jonas found himself transformed from village eccentric to sought-after advisor. Neighbors who had mocked his bear den the previous autumn now arrived with questions about stove placement, insulation materials, and entrance design. His methodical approach to construction, once criticized as unnecessarily slow, was now recognized as careful engineering. The 2 months he had spent on his original construction were understood to represent thorough planning rather than inefficient work habits. The most significant validation came from an unexpected source. A territorial surveyor visiting the valley that summer documented the various shelter types and their performance during the harsh winter. His official report, filed with the territorial government, specifically noted the superior fuel efficiency and structural integrity of the Norwegian thermal mass method, developed by Jonas Kristoffersen. The surveyor recommended that future settlement planning consider these techniques, particularly in areas subject to extreme weather conditions. Children who had once dared each other to peek into the hollow log began bringing their parents to see the interior construction details. Jonas patiently explained his techniques to anyone genuinely interested in learning, sharing the traditional Norwegian knowledge his grandfather had passed down. He demonstrated the importance of air circulation patterns, showed how the raised floor system prevented moisture problems, and taught the principles behind positioning heat sources for maximum efficiency. By the winter of 1879, approximately 10% of new construction in the valley incorporated some variation of Jonas's thermal mass principles. The hollow log tunnel itself had acquired several additions, including a small lean-to workshop where Jonas stored tools and materials for helping neighbors with their building projects. What had begun as one man's adaptation of Old World knowledge to New World conditions had quietly evolved into a recognized alternative to conventional frontier construction methods. The settlement's attitude toward Jonas had fundamentally shifted. Samuel MacLeod, now living comfortably in his hybrid thermal mass cabin, publicly acknowledged that the Norwegians' slow approach to construction had actually been the most practical all along. Rebecca Larson began referring to him as Old Cedar Jonas with affection rather than mockery, and her children grew up understanding that true innovation often appeared foolish to those who hadn't yet grasped its underlying principles. The transformation of Jonas Kristoffersen's hollow log method into accepted regional practice accelerated through the 1880s as word spread beyond the immediate Columbia River Valley. Territorial records from 1881 document similar thermal mass construction appearing in settlements throughout the Cascade foothills, adapted by Norwegian, Swedish, and German immigrants who recognized the efficiency principles behind the technique. The Washington Territorial Survey of 1883 specifically noted the prevalence of cedar cavity shelters and thermal mass cabins in counties with significant Scandinavian populations, reporting fuel consumption rates 30 to 40% lower than conventional log construction. However, the rapid expansion of commercial logging operations began eliminating the raw material that had made Jonas's original method possible. The massive old-growth cedars with naturally hollow cores, formed by centuries of heartwood decay while the outer shell remained sound, became prime targets for timber companies seeking the largest and most valuable logs. Steam-powered sawmills established along the Columbia and its tributaries could process these ancient trees into high-grade lumber far more profitably than leaving them for homesteaders to convert into shelters. By 1885, finding suitable hollow cedars within reasonable distance of settlement areas had become nearly impossible. This scarcity forced continued evolution of the thermal mass principles Jonas had demonstrated. Carpenter settlers like Samuel MacLeod began developing standardized techniques for creating artificial versions of the hollow log effect. The most successful adaptation involved building double-walled structures with cavities filled with cedar bark, sawdust, or even dried seaweed in coastal areas. These constructed thermal mass walls, while requiring more labor and materials than Jonas's natural approach, could still achieve fuel savings of 25 to 30% compared to conventional single-wall log construction. The technique's spread brought it to the attention of territorial officials and early anthropologists studying Pacific Northwest settlement patterns. Dr. William Fraser, a researcher with the Smithsonian Institution who visited the region in 1887, documented what he termed the Norwegian hollow log phenomenon in his report on frontier building practices. Fraser's investigation revealed connections between Jonas's methods and traditional Scandinavian construction techniques dating back centuries, particularly the use of thick timber walls and strategic heat placement that had allowed survival in Arctic climates. More significantly, Fraser's research uncovered the indigenous roots underlying many aspects of Jonas's approach. Interviews with Yakima and Klickitat tribal members revealed sophisticated knowledge of cedar's thermal properties that had been developed over generations. Native builders had long understood that dead cedar retained structural integrity while developing superior insulation characteristics, and they had constructed winter shelters using modified natural cavities and fallen logs for centuries before European contact. Jonas's innovation represented not discovery, but adaptation, the successful application of traditional knowledge that had sustained people through countless Pacific Northwest winters. The recognition of indigenous precedent added depth to understanding the hollow log method's effectiveness. Tribal knowledge included sophisticated techniques for selecting trees with the proper heartwood decay patterns, methods for waterproofing natural wood cavities, and principles for positioning ventilation that prevented smoke accumulation while maintaining heat retention. These techniques, preserved in oral tradition and practical application, had informed Jonas's approach through informal exchanges with native workers at regional sawmills, though the full extent of this knowledge transfer wasn't documented until Fraser's systematic investigation. By 1890, the hollow log method and its variations had become sufficiently established to warrant inclusion in territorial building guides. The Washington Territory Manual for Settlers, published that year, included a section on thermal mass construction that described both natural hollow log utilization and constructed alternatives. The manual noted fuel efficiency improvements of 25 to 40% and recommended the techniques particularly for areas with harsh winters or limited firewood supplies. The method's influence extended beyond individual construction projects to broader understanding of building efficiency in harsh climates. Engineers working on railroad construction through the Cascades studied the thermal mass principles when designing section house heating systems. Mining companies in the region adopted modified versions for heating remote facilities, where fuel costs made efficiency crucial. The practical knowledge that Jonas had adapted from Norwegian tradition became part of the technical expertise that enabled large-scale development across the Pacific Northwest. World War I brought renewed attention to fuel conservation, leading to official recognition of thermal mass construction techniques in federal efficiency programs. Government publications from 1917 and 1918 specifically referenced Northwest hollow log methods as examples of traditional knowledge that could reduce heating costs for civilian populations. These wartime efficiency drives helped preserve documentation of the techniques, even as changing construction practices and urbanization made their practical application less common. The hollow log tunnel itself survived until 1923, when Jonas's advancing age and the availability of modern housing led him to abandon the cedar structure that had sheltered his family for 45 years. Local historian Martha Whitman documented the tunnel's interior before its abandonment, noting that the thick cedar walls remained sound and the heating system still functioned efficiently despite decades of use. The structure stood empty for several years before being claimed by forest growth, leaving only foundation stones and scattered metal hardware to mark its location. Modern analysis of Jonas's achievement reveals principles that anticipated later developments in passive solar design and thermal mass construction. His intuitive understanding of heat storage and release, learned from traditional Norwegian methods and refined through direct experience, paralleled concepts that wouldn't be formally codified by building engineers until the mid-20th century. The fuel efficiency he achieved through careful positioning of heat sources and strategic use of thermal mass exceeded performance standards for conventional construction by margins that remained impressive even by contemporary building standards. The fundamental lesson embedded in Jonas Kristofferson's hollow log tunnel transcended its specific technical achievements, demonstrating that traditional knowledge, properly understood and adapted, often surpassed methods considered modern and progressive.